Our next speaker is Dr. Mahidhar Tatineni. Mahi has been leading the user services group at the San Diego Supercomputing Center over the last decade, and he's been collaborating with the MBAPICH team for almost 19 years now, Mahi.
Yeah, quite some
So
time.
Mahi will be talking about his experiences in using MBAPICH Plus with different partitioning modes on the SDAC Cosmos system. Let's welcome Mahi.
Thanks, Hari. I think I need permission to share. Let me see.
Yes, you should have
okay.
it now.
Okay. Let me see if that works. Did that work okay?
Perfect. Maybe you want to go to the full screen mode?
Yeah, I will. That looks good.
Yeah, perfect. Thank you.
Thanks. Thanks, Hari. And yeah, thanks for the invite. And yeah, we've been working together for a long time. So hopefully that continues. So yeah, I'll basically talk about the different partitioning modes on Cosmos that we test out and some of the application performance. Unfortunately, the machine's actually down for update, so I don't have the latest results, but I can give you a flavor of how things look. Let me go to the next slide. So Cosmos itself, it's a Category 2 testbed system that is supported by an NSF award. And the PI on the system and co-PIs are Suba, Andreas, Igor, and Christopher. Is basically the first system on the NSF landscape to expose an accelerated processing unit. So the AMI 300A from AMD essentially features unified memory between CPU and GPU, and I'll go into the details a little bit more going forward. One of the things with the Category 2 approach for NSF systems is the first 3 years are a testbed phase. So that's what we are in with Cosmos right now. We are in the first year of the testbed phase, where essentially we are trying out things and have a limited engagement, but with engagement with a limited number of people to kind of try out the features and see what works, and then it gets into the allocation phase in the last part of the project. Our goal with Cosmos was to try and make it easier for people to use accelerators, and with the unified memory, we were hoping that it would facilitate a incremental programming approach so that the porting aspect is a little easier. But it works fine with existing GPU codes, and if you have a HIP-based code or with an OpenMP offload approach, both ways, existing codes should work fine, but we were targeting new people to use accelerators. The machine itself is a Cray EX2500 with HP Slingshot interconnect. It's a 4-socket node, so 4 APUs per node. And basically, it's got 4 NICs per node also, so for high bandwidth between the nodes. We have a flash-based VAST file system, and we're targeting applications from a wide variety of communities. So the architecture itself, the MI300A APU, and you may have seen this already, but I just want to go over it just for completeness. Like it combines the CPU, GPU, and memory on a single package. If you look at the picture on the right, there are 6 accelerated compute dies, which are essentially GPU capabilities, and a total of 228 vector cores. And then there is a 128 gig of HBM3 memory that's coherently shared between the CPUs and GPUs. And the CPUs on this chip are essentially 24 Zen 4 EPYC cores. There is a 256 megabyte AMD Infinity cache that is shared between the XCDs and the CPUs. And we are hoping the design will eliminate the need to do host device data copies and ease the code development as a result. So Now, the interesting thing is these XCDs can be exposed in many different ways and different partitions. So that's what we were trying to explore actually with some of our testing. Uh, so the AMD has three different options. So the first one here shown here is the single partition accelerator or the SPX mode. Basically, it takes all 6 XCDs and combines them into a single logical GPU device. So you will see all of the resources, that 228 compute units and the 128 gig of HBM as a unified pool as one GPU essentially. So if you log into the node and do an AMD SMI, it's going to show one GPU per APU. So on Cosmos, because we have 4 sockets, you'll see 4 GPUs on a node. This is useful if you need a lot of memory, like say a monolithic workload, like a large deep learning model or something like that, that can utilize all of the memory and the resources. And it basically provides the full memory bandwidth of all the channels together, unified addressing and hardware level synchronization. And also you have the unified last level cache. This is what the default mode is on Cosmos. And originally when we were in the testbed phase, we found some instabilities with the other modes. So we didn't initially go into that mode and we ran with the SPX mode as the default. So currently that's the default. The next mode is a triple partition accelerator or TPX mode. This divides the APGP capabilities into 3 partitions, each with 2 XCDs. So this results in 3 logical GPU devices per APU. And each of these partition gets 76 CUs and 32 gigs of HBM memory. So it's good if you have a modest amount of, I mean, you don't moderate amount of memory need per task, and you can scale out a little bit. And so on Cosmos, you will see 3 GPU devices per APU. So you will see 12 GPUs in this mode. And all the partitions maintain full memory coherence and uniform memory access. One thing to note here is these modes right now, we don't have it set up as a slum option. So what we do is reservations and make them available to users via reservation. So we set the nodes to the TPX mode, and I think 4 nodes are set up this way on Cosmos. The last mode is the core partition CPX mode, which basically divides the APU into 6 partitions and exposes each XCD as a separate GPU device. Each partition has 38 CUs and 16 gigs of HBM memory. This is really useful if you're running multiple lightweight jobs concurrently or running a job that scales well but has lots of coupled parallel tasks. And in this case, the AMD SMI will show 6 GPU devices per APU, and you'll see 24 GPUs on the node. Peer-to-peer access between CPX partitions is supported and can be enabled. And it's also useful in multi-tunnel kind of scenarios if you need workload isolation. And details of all this are in the Instinct docs that are linked there. So that's kind of at the chip level. The typical 4-node architecture is shown here. Basically, the 4 APUs connected using XGMI, and we have the 4 slingshot NICs as well in our case. All of this goes into a single rack of EX2500. It's a completely liquid cooled system, I think about 130 kilowatts in the rack. And we have 42 nodes populated on Cosmos. So from a programming standpoint, we are hoping this is going to make things easier. As I mentioned, the memory movement is not needed. You can port 1 loop at a time, for example, and interleave CPU and GPU work, and lots of different approaches. You can use HIP if you want, OpenMP, and also scalable frameworks like Cocos and Raja. And There's lots of different compilers available. GNU and Cray kind of are the default setup on Cosmos. And as I mentioned, if it's already ported using HIP, you should be able to run the code. And actually, the examples I'll show you today are in that category. I'm going to skip the Rockham slide because it's kind of just showing you the overview of how it's set up. Just from a programming model aspect, this kind of shows you how it makes it easier. If you had a CPU code in the traditional OpenMP offload approach, you would have had to map the memory on the GPU and move the data in and then do the parallelism. In the APU case, you can essentially target that memory either from the CPU or GPU, so it's a lot easier. So current status, it's in that first year of its testbed phase. We did a lot of acceptance testing last year, and I think I presented some of the results last year with some of the standard codes we run, like HPL, Amber, Unifrac, CGyro, which has a HIP FFT requirement, and IceCube benchmark, and some AIML benchmarks. MBABIC Plus on Cosmos has been there almost since the start. The Pandas group has been on since the early user testing phase and are continuing in the testbed phase on Cosmos. We are testing with GNU compilers and MBABIC Plus. The Cray compilers are tricky to separate out for MBABIC. So right now we don't have that as an option. For the GNU compilers, early in the testbed phase last year when I presented, I think we were using the default OS compilers for the same kind of reasons. We were having a difficulty separating out the GNU compiler from the Cray stack, MPI stack. But we now have the MBABIC Plus GA version, 4.1 GA version with the new compilers as well. Just a quick look at the latency and bandwidth numbers, pretty much as expected there with the performance. I'm not going to go too much into the detail, but Dr. Panda's group, Gautam, and others have a very detailed paper that I have linked below there that they have their results from, I think, both Cosmos and Telomnia probably. So going to what I wanted to talk about today, we actually started getting into this because we were testing out a Monte Carlo dynamic code. MCDC is the name of the code that for a different project. It's a Python-based Monte Carlo radiation transport software package. It's essentially designed for like rapid development and scalable execution, and essentially does the parallel execution using MPI for Pi. Right now, I actually tested this only with MPI, not MBABIC testing is kind of ongoing right now. But the results are going to look similar, I think, because this code doesn't do too much intensive MPI communication. The backend on the GPU functionality, it's essentially using HIP-enabled number for that. And there is a Kobayashi 3 TD benchmark that essentially looks at neutron transport in a purely scattering, absorbing shield setup. And this is an easy problem to scale up using the number of particles. So it was kind of easy to do weak scaling tests. And on Cosmos, we tested this in the SPX, TPX, and CPX mode. And if you want more info on MCDC, you have the link there. So right out the gate, we just tested using just one MPI task per logical GPU. So that means if I am running in SPX mode, I have one MPI task per APU. If it's TPX mode, is 3 MPI tasks per APU, and CPX has 6 MPI tasks per APU. And the plot on the right shows the simulation time in minutes and scaling out from 1 APU all the way to 32 APUs, which is 8 nodes on Cosmos. And you can see that clearly the CPX mode where we have 6 GPUs per APU has the best performance with under 2 minutes of simulation time. And there's a pretty huge, almost a 2x difference between the SPX and CPX mode. So, I mean, that there could be lots of reasons for this. So we wanted to first thing try basically just increase the number of MPI tasks in the SPX mode and see if we can fill up the APU more, which is the next set of results. So this is basically running in the SPX mode, but just increasing the number of MPI tasks. So it's 1, 2, 3, and 6. And you can see that we do definitely see an improvement with the 6 MPI tasks per the APU in the SPX mode, but it is still above 2 minutes in the execution time. And if you go back to the previous plot, you can see in the CPX mode, we were doing better even with the same number of MPI tasks. Of course, in the CPX mode, the memory locality will be a lot better, I think, because of the layout and the controllability. Like on this SPX mode, really, we don't know where the 6 tasks land, which section of the APU they're using. And we essentially depend on the inbuilt AMD kind of distribution of that. And the memory layout is quite complicated, actually, if you look underneath. So it's possible there are differences due to that. And we essentially have to do more in-depth profiling to figure out where things are landing, actually, in terms of both the compute pieces and the memory and on the underlying XCDs, essentially. And this is true even for the 3 MPI tasks. For example, if you look at the TPX mode, you had under 2.5 minutes in the previous plot. And if you look at the 3 tasks on the SPX mode, it's still above the 2.5 minutes. So in both cases, you can see using the unified mode with 1 GPU per APU is slower compared to the more fine-grained approach in the partitioning. And this was something that I saw with lamps that I presented, I think, last year. Basically, we built lamps using MVAPage Plus and with essentially 2 different kinds of builds, like a hip-based approach and MPI and GPU hip-based packages, or with COCOS. There we again tested with the SPX and TPX mode, and this kind of shows you how you see the processes on the SPX and TPX mode. So at that time, the CPX mode wasn't available on Cosmos because we were having some trouble with it, but now that is available. So I'm going to repeat this with the CPX mode. But you can see the performance, and in this case, we are looking at nanoseconds per day, I think, and that is better in the TPX mode, but quite a bit actually even with 1 and 2 APUs here. So we are planning more runs in this as well. But one of the things I kind of realized is there's not much MPI communication in the MCDC code, at least for the test cases that we were running. So I'm going to try out the GROMAX build and testing. This is ongoing right now. This is an open source software suite for high performance molecular dynamics, and we are testing this on both Tulumne, which has the same kind of nodes and network, and Cosmos using the HIP-enabled GROMAX. And I'm going to test this with both MPage and MVAPage and compare performance. So I think on Tulumne, you just have the SPX and CPX options. So we'll try those there. And on Cosmos, we have a bit more control. So we're going to try out all the modes. And the build is adapted from Lumi, which also features AMD GPUs. And I have the link down there if for the GROMAX build. So this is ongoing work. So to quick summary, basically, Cosmos makes this interesting MI300A APU available for the NSF community. Hopefully, a lot more open research happens with that. Uh, System is in testbed phase, and we do work with researchers closely in this phase. So if you're interested, and I have the next slide with how to get in touch with us. And the APUs can be partitioned in different logical GPU counts. So the SPX with 1, TPX with 3, and CPX with 6. So far we are seeing that the CPX mode is doing the best in most cases. And we've tested it with various partition combinations for MCDC and lamps. GrowMax is in progress. But I think we need detailed profiling to kind of get more insight into why this is happening, even with the same number of MPI tasks per APU. Thanks for everyone at STSC who's made this project happen, and thanks to Dr. Panda's team and Mbappe's team for continuing to provide all these performant versions on our systems. Thanks.
Let's thank Mahidhar.
Yeah. And quick thing on allocations, if you're, we are in the testbed phase, you can contact us at consult@STSC if you have a project that might be a good fit. We can follow up, collect info on your project, and evaluate if it fits with what we want to do and give you access. So thanks.
Thank you, Mahi. Do we have any questions for Mahi? I know we are in the awkward position of standing between you and lunch, but still.
Yeah.
Yes, Gautam.
Hi, Mahidhar. This is Gautam.
Hi.
So I have a quick question. So it's a nice presentation, first of all, and it's very interesting. So I just wanted to know, did you try to use more than 3 ranks or more than 6 ranks on SPX partition and see how it is scaling up, or like, so basically traditionally we use generally 1 MPI rank per device, right? And this clearly it means that like one MPI is not able to use the complete computation power on SPX partition. That's what I think.
That's what it looks like. Yeah. So I haven't tried more than 6. But like you see, it's not just that, like, because there's also some kind of memory locality thing going on, I think, because even with 6 tasks, I'm not getting to the same performance, right? And I haven't pushed both of those. I mean, I could do that on the CPX mode too, for the MCDC code, because that's a pretty scalable code. So I don't know if you've tried it yourself with more tasks, but that's something interesting. You definitely can try it out and see what happens.
So does that mean in CPX partition, like when you're allocating memory, it is closer to the appropriate APU or XCD? Is that what like you?
Yeah. So the underlying architecture, I think the memory channels are bound to the closest XCDs, I think. I mean, the XCDs are bound to the closest memory channels, if I understand it right. Whereas in the SPX mode, it's kind of all combined, right?
Yeah. Okay.
So there may not be a balance. Like I think the CPX mode will ensure that there's equal balance across all the memory channels, I think.
Okay. So yeah, I think maybe having a control of where the memory gets allocated makes SPX partition much better maybe than.
Yeah, so that will, and I don't know if there is a mechanism within the SPX mode to kind of do more careful layout of tasks, because it's sort of opaque to us, right? At least from what I can see. And I think that's something I'm going to probably ask AMD more about, like, and see if there are other options to better place tasks. But definitely it's interesting. And all of us actually, I think even the El Capitan system initially started off in the SPX mode, but I think now they have both modes available there, right? The CPX and SPX. So, and I think they saw something similar with most of the codes. Is the CPX does better, I think.
Yeah. Thanks, Mahidhar.
Yeah.
So thank you, Mahi. We are bang on time for lunch. So let's thank the speaker again.
Thanks. Thanks, everybody.
Thanks, Mahi. So
Thanks.
we have